Okay, today's video is an AS level physics exam from the Edexcel linear course. It's core physics 2, so the main topics are waves and materials, but at the end they can ask, the last two questions can be on any of the topics in the year, so it could also be on waves, it could also be on electricity or mechanics. Okay, so I'm going to upload this because I think AS Core Paper 2 is next week. So Wednesday next week is the Core Paper 2 for those of you taking the AS level. And for those of you preparing for A level, next year this is a good practice exam. Okay, so let's get straight into it. So it starts off with 8 multiple choice questions, and it starts question 1. The graph shows how the displacement of particles in a progressive wave varies with the distance along a wave at a particular instant. So time is fixed, and this is a snapshot of a wave, so it's basically displacement on the y-axis along the distance of the wave. The question asks, which of the following is the phase difference between the particles at S and at T? So you can see that there's a difference between them of half a wavelength, because a full wavelength would be from there to there. So there's a difference of half a wavelength, so half a wavelength in terms of radians, which if it's got pi in it, it means they've changed to radians. A full wavelength is 2 pi. Yes, a full cycle is 2 pi, and it's half a wavelength. So you divide 2 pi by 2, and therefore you will get the answer is pi. So you want to put your X in C. Question 2 is 2 diverging lenses combined as shown. The focal length of each is 0.2 meters. So they've told you the focal length, and they want you to work out the total power of the combination of 2 lenses. Okay, so power and focal length are inversely proportional, so there's the equation for power and focal length. And diverging lenses have negative power. Okay, so if you put 1 over F, it'll be 1 over 0.2, so that'll be 5, plus 5, 10, but it'll be minus, so it'll be minus 1 over 0.2 plus minus 1.2 again, so the answer will be D minus 10. Okay, so it's minus 5 plus minus 5. 3, an electron in an atom absorbs a specific amount of energy, and it gets excited in that it moves up one energy level, from one energy level to the next. When the electron returns to its original level, a photon is emitted. So this is this is how photons are produced. So they want you to work out which of the following would be a mathematical expression for the wavelength. Okay, so the equation linking energy and wavelength is hc over lambda. Okay, so once you know that, then you should be able to determine that if you make lambda the subject, you'll get lambda equals hc over E. So you're looking for hc over E, so that is A. There we go, there's a multiple choice for the first 4 questions. We haven't met question 4 yet. So the answer to 4 we can see is B, and let's see why. So the image formed by a lens can be described as real or virtual. Which row describes a real image and a virtual image? In other words, which row has both definitions correct? So basically a real image can be produced on a screen, so we're looking for B or D. Okay, So whenever you see a real image, just remember it can be projected onto a screen. And the virtual image is formed on the same side of the lens as the object. And that's why it's a virtual image. It's not really there. So we're looking for forms, so it'll be either of those. So once we know that B has both ticks, you can get the right answer. So you can see that here they've talked about can be produced on a screen, which is obviously not a virtual image, because it's not really where you imagine it to be. Okay, it's not correct. So the answer is B. Okay. So they basically used the same two variations, and you've got to get them the right way around. So multiple choice questions are a great way to revise and discuss this with someone else doing the same exam, because it makes you think. The photoelectric effect is the next question. Provides evidence for the particle nature of electromagnetic radiation. So which of the following is not? So they always underline it when it's not observed in the photoelectric effect. So I put the ones which is observed as ticks. Photoelectrons are released instantly. Yes, it's an instant process. So when an electron absorbs the photon, if it's got enough energy, the photoelectrons will be released instantly. There's no time delay. And B says photoelectrons are only released above a certain frequency, the threshold frequency. So that's correct as well. And let's go to D, because D is also correct. The energy of photons is proportional to the frequency. That's correct, because energy of photons in joules is equal to Planck's constant times F. Okay? So the only answer it can be is C. So let's read C. It says the energy of photoelectrons is determined by the intensity of the light. No, it's just determined by the frequency, not the intensity of the light. So this one is incorrect, and the reason it's incorrect is because of the word intensity. Intensity, when we're talking about the particle nature of light, the intensity just means more photons are coming per second, okay? But the energy of the photons is not increased by the intensity, you just have more of them. So therefore the energy that the electrons will gain will be all the same. So the intensity does not increase the energy of the electrons. So the answer is C. Question 6 is about units. Which of the following is the SI base unit for breaking stress? So you want base units. Base unit means kilograms, meters, seconds, and whatever else is a base unit you need to know. So those are the only three you need for this question. So for breaking stress, so stress is force over area, and you should be able to work out the force is kilograms meters per second squared, because it's mass times acceleration, divided by the area meters squared. So you're going to get kilograms meters to the -1, s to the -2 if you simplify it. So the answer is D. Okay. Question 7. A ball bearing with radius r falls through a fluid with density rho. Which of the following is an expression for upthrust? Well, upthrust, you need to know, is the weight of fluid displaced. So the mass would be volume times density, and then you've got to multiply it by g to get the mass into newtons. Yes, kilograms to newtons. So that's basically mass times gravity. The volume is 4/3 pi r cubed. Yeah, and there's density, there's gravity, so we're looking for 4/3 pi r cubed rho g. Looks like B, doesn't it? 4/3 pi r cubed rho g. 7 is B. Now, this was about polarization or unpolarized light. Unpolarized light is when the light is vibrating in all angles. at all angles, not just in one plane. When unpolarized light passes through two polarizing filters, as shown, the planes of the polarization of two filters are aligned. That means they're in parallel, so the filters are in alignment with each other. So if it can go through one, it can go through the other. One filter is rotated, so the planes of polarization are now perpendicular. Yeah, so therefore one will block the horizontal components and one will block the vertical components. So you're going to end up with nothing. It's going to fall to zero. Okay? Before it would have been half intensity approximately. Okay? So it's B. That's the end of the multiple choice in AS Core 2. AS Core 2, unlike the International A-Level, only has 8 multiple choice. The International A-Level has 10. Okay, so there's how they give it in the mark scheme. They don't really give you that much explanation, so hopefully my run-through will help you. Question 9, another question about lenses, okay, which is not in the International A-Level. So if you're looking at this as practice, general practice, and you're doing the IAL, lenses are not in the International A-Level. Here you got a telescope, which is used to produce a magnified image of the full moon. Okay, so when the full moon is sending light in, it's quite far away, so they come in parallel. Okay, so imagine the moon is up there somewhere. There's the moon, and it's giving light off, and they're drawn two rays. One going through the center, which is undeviated, yeah, and the other coming higher, and that will refract. So you're going to get some refraction. The telescope consists of two converging lenses. Yeah, the objective lens and the eyepiece lens are both converging. The objective lens and the eyepiece lens are arranged as shown. Yeah, so the observer is looking from here, and they're going to explain. The objective lens produces an inverted image, that means upside down, at point X, so it's over here. The image at point X is then the object for the second lens, the eyepiece lens. Yeah? So because it's quite close to the eyepiece lens, the second lens acts a bit like a magnifier, a magnifying glass. That means it must be closer than the eyepiece's focal length. And when that happens, you get a virtual image the same way up as the image at X, magnified. Okay, so that's basically what they're saying. A magnified image. The power of the objective lens is 0.8 diopters. And remember, power is equal to 1 over f. So you can work out that the focal length of the objective lens is 1.25 meters, 1 over 0.8. Okay? Now the distance, they want you to calculate the distance of the image at X from the objective lens. So how far away is it? So you know, this is the main equation for lenses. 1 over the focal length, which I just worked out for you. Yeah? So you put that 1 over f in there. And we want to find out 1 over v. So we know that 1 over u, because u is a distance to the image, to the moon, and u is a very large distance, so you can assume that 1 over u can be assumed to be 0, or very close to 0. So this tends to 0. 1 over f we know, so 1 over v will be equal to 1 over 1.25. Yeah? So when you inverse them, the distance to x will be 1.25, because rays from very distant objects like the moon will converge also at the focal length, so you should have realized that that is equal to the focal length, which we worked out before. Okay? And that means we don't know how far apart, for example, this distance, we don't know it, but it would be less than the focal length of the eyepiece lens. Okay? So we just worked out that this is 1.25 meters from here to here. Okay. Now they want you to complete the ray diagram to scale to determine the magnification of the image formed by the eyepiece lens. Okay, so we know that we want to find V. Basically, as I've drawn it, we want to find V. Okay, we know the image is over here, and we can draw one ray going through the center of the lens, because this is the lens. Yeah, this line here is the eyepiece lens position. So when it goes through the center, there's no refraction, so that ray is always drawn straight through without any deviation, without any refraction. The second ray you always draw is drawn to a position below at the same height, or in this case, it's going downwards, and it comes parallel. Okay, and when you do that, the parallel light will go through the focal length of the eyepiece lens, which they've given us. And then the eye, if you're looking from over here, there's your eye, you're looking at these two rays, then will converge where the image position will be the magnified image position. Okay, so once you do that, you can work, so you always draw one ray going straight through and one ray going to the height of x, and if it's going parallel to the principal axis, which is here, then it will go through the focal length. Okay, so to work out the magnification, which is what they want us to do, they want you to work out V over U. Yeah, so you can measure V in terms of your squares, because if you've drawn it with the rays going the way I said, so imagine that he's looking as if the rays are coming through here. Yeah, they converge there, so you can work out with a ruler how many squares that is. Yeah, because it's drawn to scale, and you can then, you know that U was 3 squares and this one's 7.6 squares, so basically it's a ratio of 7.6 to 3. You can also do it by the height of the arrows, it should give you the same answer. Okay, but it's easier to count the squares along because they're bigger than the image, so the distance to V and F, as I've drawn them, are larger than the height difference, so you're going to have a smaller uncertainty by doing this way. So to 3 significant figures is 2.53, and you can round it to 2 significant figures to do question 9. Hope that makes sense. There's the mark scheme. So as I said, this is what we just did. 2 rays drawn, extended line joining the center of the lens to the tip of the object, and then a horizontal line from the tip of the object to the lens, then extended line joining the point of the lens where this line intercepts the focal point on the right side of the lens. Okay? Okay. And then the image is where these 2 rays meet. Okay? And then you can either do image height over object height, but I think it's better to do it this way. You'll get closer to the true answer, and they're giving you a value of between a range of 2.3 to 2.7. So we got 2.5, or I did 2.5 when I drew it. Okay. Question 10. Scientists use pulse echo technique with ultrasound to detect plastic in oceans, and here is just telling you a transducer emits and detects ultrasound pulses and is positioned just below the surface of the water. Okay, so the ultrasound pulse was transmitted, the pulse was reflected from a piece of plastic under the surface, and the pulse was detected 4.1 milliseconds later. That means it's gone there and back, so it's the time it's taken to get to the plastic and come back to the transducer. Okay, calculate the distance between the plastic and the transducer. So basically you need to realize that it comes from the surface of the water, bounces back, so it's gone, the time to go there will be half. So you can divide the time by 2 to get the time, and we know the speed is given to us in the question. You multiply the speed by the time it takes to go to the plastic, and you get 3.08 meters. If you do 3 significant figures, yet again, you should round it up to 2, because the data provided is only given to 2 significant figures. Give a reason why the ultrasound is emitted in short pulses. Well, you're going to constantly be sending them out, and you're looking for the echo to return, so we don't want the pulses to overlap, otherwise you'll get confused as to which one it was. So the reflected pulse should return before the next pulse is transmitted. Okay, basically it's looking for echoes. So, explain why small pieces of plastic are more likely to be detected if you're using high frequency ultrasound. Okay, so this is about having more resolution, the ability to detect smaller objects requires a high frequency, because a high frequency means a shorter wavelength, and a shorter wavelength means a better resolution. Basically, the resolution is it can detect smaller objects. That's what resolution means. For example, a micrometer has a resolution of 0.01 millimeters, and calipers digital have 0.1 millimeters. That's what resolution means. So you can get more detail out of it. So you get greater detail can be detected if you have shorter wavelengths, therefore higher frequency. Hope that makes sense. There's another 6 marks done in this run through. There's the answer. They're also allowing you to say shorter wavelengths diffract less around small objects. Okay? Now, I don't like that answer as much as this. I think that will confuse students more than the way I've explained it. Question 11, a technician shone light from a laser through a diffraction grating. The pattern was observed on the screen 4 meters away, which is normally the distance you can get with the laser. It's bright enough to get 4 meters away, which allows you to get a better determination of the angle. The pattern consists of 5 maxima as shown, central one, and first order on each side, and second order on each side. So we know the diffraction grating equation is n lambda equals d sine theta, where 1 and 2 are the n, okay? And they say the diffraction grating has this many lines per millimeter, okay? So if you know the lines per millimeter, you can then work out how far apart each of the slits in the diffraction grating are. So it will be 1 over 400, and that will be in millimeters, but you will need to put it into meters for the calculation. The technician wanted to check the wavelength emitted by the laser was within the range 450 plus or minus 10 nanometers. Okay, so they want you to check that you get that value. In other words, is lambda between 440 and 460? Okay, because that would be plus or minus 10 each side of 450 nanometers. You need to know that nanometers is 10 to the minus 9. She measured the distance between the two second order maxima as 3.25 meters. That's a good scientific method to go from the second order on each side, and then you can work out the angle from the central one by dividing 3.5 by 2, because this is the angle you want. Okay, the angle subtended between the center and the second order. So 3.5 divided by 2 will give you 1.625 meters. So that's the angle here. That's the distance here. I now deleted it. So that one, we know this is 4 meters. We don't know this, but we do know, I'm going to draw it in green, from here to here, then is 1.625 meters. Okay, so that allows us to use tan theta to divide 1.625 by 4 meters, which will be opposite over adjacent, which will give you a theta of 22.11 degrees. Okay, so now we know they want us to deduce for the second order, so we know n is 2. We worked out theta is about 22.1 to 3 significant figures, and we can then work out 1 over 400 is 2.5 times 10 to the minus 6 in meters. So you've got to change that into meters. Okay? So we want to find out lambda, so you can divide d sine theta by 2, where n is 2, put the numbers in, yeah, and you'll get 4.7 times 10 to the minus 9, so it's 470 nanometers, which is outside the plus or minus 10 range, so that's what you've got to conclude. Okay, so whenever they ask you to deduce something, you've got to then go back and respond to say that it's outside the range that we were looking for. Part B, it says that electrons in an electron beam have an approximate speed of 10% of the speed of light. So we were given the speed of light, so it's 10% of 3.0 times 10 to the 8. So we know that these electrons have this speed. So whenever they're talking about that, it's often going to be de Broglie. De Broglie's equation is the wavelength of the electrons will be h divided by the momentum. Yeah, and the mass of the electrons is given to you on a data sheet. So you can automatically calculate the wavelength to be 2.4 times 10 to the minus 11 meters. Okay, so one for getting the speed, one for getting the wavelength. So it is possible to demonstrate diffraction, it says, yeah, with electrons, yeah, when the electron beam is incident on a graphite target. Okay, so a graphite target works as a diffraction grating for electron beams. If the spacing of the atoms in the graphite target were equal to the spacings, however, of the diffraction grating used by the technician for the light, yeah, that would have been the gaps between the diffraction grating that we used in part A. This electron beam would not show any diffraction effects. Okay, you've got to explain why. Yeah, so it says your answer should include calculations. So it means that using the calculations, de Broglie, we work out that the wavelength of the electrons is about 10 to the minus 11 meters, whereas if we use the diffraction grating that we were using in part A, that's 10 to the minus 6 meters. So diffraction will not be observed because you need the wavelength and the gaps that they're going through, which will be the slits, must be approximately the same size. So since lambda is much, much smaller than the diffraction grating that we used in part A, by a factor of 10 to the 5 different, you will not get any diffraction. So you have to remember for diffraction, the wavelength must be approximately the same as the gaps. Okay? That's question 11 done, and there is the answer. Okay? Let's do question 12. I'm on a roll. A student investigated the properties of metal wires. Yeah. So he had to determine the diameter of the wire. What should he use? He should use a micrometer screw gauge. That's the full name. Because it has resolution of 0.01 millimeters. Yeah, you always determine the diameter of the wire with a micrometer screw gauge. And then you should make sure that you repeat the measurements, because wires are not perfectly symmetrical in terms of it's just made by a machine. So you need to do it at different points along the wire and at different angles, different orientations, because it won't be a perfect cylinder, and then calculate the mean diameter of the wires. Okay, they're made to be within a certain range of diameter. It's called a standard wire gauge, so it's called an SWG, so they're designed to be a certain diameter, but you've got to check them several places to make sure. Okay, so this is 3 marks for this question, how they should do it. The student then applied increasing force and determined the corresponding extensions of the wire. Okay, so they got force on the y-axis and extension on the x-axis. Okay, the force was applied in increments or intervals of 5 newtons up to a maximum value of 40 newtons. So they went up to 40 newtons max, and you can see that there's a straight line portion and then it starts to exhibit deformation. So whether it's gone beyond the elastic limit, probably the elastic limit will probably be around here. So the proportionality limit is probably around there, and the elastic limit is a bit further. But if you go too far where it starts to curve noticeably, then it will not return to its original shape. Okay. So it says the Young's modulus of the material is given by gradient of this line, which is the gradient of this line will be force over extension. Okay, so they're saying you can work out, if you can work out the gradient and then multiply it by the original length and divide it by the cross-sectional area, you can work out Young's modulus, which is true. Yes, because Young's modulus, you should know, is stress over strain. So it'll be force times force times, so I'm just rearranging it to show you. You got now force times length on the top and area times extension on the bottom. Yeah, so you can see that force over area is stress, and extension, I think we got it the wrong way around. Yeah, gradient times x over a. Force times length, area times extension. That's correct. Okay. So you will notice that it's stress over strain, of course, because this is 1 over strain. Yeah. So that'd be 1 stress times 1 over strain is the same as stress divided by strain. Okay. So they're giving you that, and you're going to use it in a minute. And you can see that I have put my gradient on this graph because I think it's the clearest place to show your working. So the change in force, I've done it up to here. I've used 33 here, and because that's a nice value here. So basically I've got 33 minus 0 because it goes through the origin, and the extension is 70 minus 0 because it also goes through the origin. So you got the extension and you got the force, and you divide one by the other and you get the answer. So this is what I was showing you, that Young's modulus is stress over strain. So they want you to derive it. So this is how you do it. So stress is force over area, and strain is delta x over x. So if you do stress F over A divided by strain delta x over x, and you just rearrange the equations, you will be able to show that F over delta x is the same as the gradient. So that's equal to m times x over A, where m represents the gradient. Okay, so you've proven it. You've derived the equation. It then says the value of the Young's modulus for some metals are shown in the table, and you've got to deduce which metal the wire is made from. Okay, they're giving you the values that you need to put into the equation, and they want you to find the gradient from the graph, which I've already done, using a large triangle. If you use a large triangle, you'll get this mark. If your triangle is too small, you may lose this mark. So once you do that, you divide the 33 that I showed you newtons by that, you get an accurate value, 5 significant figures, a calculated value, if you like, of 4,714, and then you multiply this gradient by the values here, and you then just put the numbers in, and you get the answer of 1.24 times 10 to the 11 newtons per square meter, which is approximately 120 gigapascals. Why am I doing that? Because the data is given in gigapascals, and 120 is quite close to copper, which is only less than 3% uncertainty. Okay, is approximately equal for the copper in the table. Yeah, 3 out of 120 is pretty damn close. Okay, and here you got the mark scheme for question 12. I'll let you stop the video if you want to take a closer look at it. Alright, so I'm going to stop the video at this stage. Oh no, we got one more part, so I'll do this and then I'll stop the video. The student repeated measurements of force extension and extension for a thinner wire. Yeah, so same metal, same length, just thinner. So only one variable change. He changed the values of the force he applied to the wire. Why did he do that? You've got to explain the two changes that the student should make to the values if he's using a thinner wire that he's applying to the wire. He needs a thinner wire, so smaller force is needed because a thinner wire will stretch more easily. So you want to avoid exceeding the limit of proportionality before you got data. Yeah. So the student should use smaller increments of force as well. Okay, so these are the two changes. Well, and the explain part is different from describe part. So first you say what you'll do, yeah, and you've got to explain it. So thinner wire, so smaller force is needed to avoid exceeding. So this is the explanation, the limit of proportionality, yeah. And then she should use smaller increments to obtain sufficient readings before the proportionality limit, yeah, or the elastic limit is exceeded. Otherwise, you won't be able to produce a good graph. Okay, so for A level, we want at least 8. For GCSE, I say 5, so you can measure the gradient in the linear portion of the graph to work out whatever you need to do. So that's standard practice for A level. 8 pieces of data would be my recommendation. Okay, well that brings me to the end of this first part of this video, the run through. Here's the mark scheme for that final bit. If you find it useful and you know other people doing the linear, I've recently started teaching the linear again. I was teaching the international A level, so most of the videos and most of the subscribers are following it for international A level. So if you know anyone who's doing the linear, do help spread the word. I'd be very grateful. Don't forget to like and share and subscribe. Catch you in the next video. Bye for now.